Okay, so we are now going to start graph theory from the book Graph Theory by Reinhard Diestel. So the first chapter is the basics. Now before we have a look at the first section, let us fix the notations and terminology that we will be using in this book. So we start with the set of natural numbers. As usual, this denotes the set of all natural numbers including 0. This is the important point. Okay, so it's the exact same thing that we have already seen in the book Analysis 1 by Terence Tao. For Terry Tao also 0 is a natural number, or the natural numbers start from 0. However, in Herstein's Topics in Algebra or David M. Burton's Elementary Number Theory, natural numbers start from 1. Now it's a matter of choice. We have already discussed about it before. It's a matter of choice whether you want to call 0 a natural number or not. It does not make any difference in the mathematics whatsoever. Okay. Then this set Z by NC or Z by NZ, which we know as the set of integers modulo n, is denoted in this book by the symbol Z suffix n. And we know from algebra what integers modulo n are. They are not ordinary integers, they are congruence classes modulo the integer n. Congruence classes modulo n. And the elements in this or this same thing, they are denoted by this symbol I bar, where I is an ordinary integer, and by definition I bar is this congruence class I plus n c, and by definition this is the coset of the subgroup nz in the additive group of integers, which equals this nk, where k is an integer. If one observes carefully, this is the set of precisely those integers that are congruent to I modulo n. Okay. Now after this, so these are things we will be needing in this book. This is not even the basics of graph theory, it's only the notations and terminology of the most basic things that we need even before starting graph theory. Then say we have a real number x, then by this symbol we mean the greatest integer less than or equal to x. I am writing in short like this. And by this symbol we mean the least integer greater than or equal to x. The function that maps x onto this integer is also known as the floor function, and this one is known as the ceiling function. There each one of them has real number input and integer output. Okay. Then logarithms written as log r taken to the base 2. The natural logarithm is denoted by ln. Okay, so if we see log without any number as suffix, then we have to assume that the base is 2, and natural logarithm by the base is the transcendental number e is, as usual, it's denoted by ln. Okay, now comes partition. Say we have a set B. B is a set, and say this is a collection of subsets of B, A1, A2, etc. up to AK. So each AI is a subset of B, and it has 3 properties. The first one is that each AI is a non-empty set. That means each set in this collection is a non-empty set. There is no empty set in the collection for all I lying between 1 and k. The second property is that the sets in this collection are pairwise disjoint. That means if we choose 2 distinct sets from this collection, say AI and AJ, I not equal to j, but each of I and j varies from 1 through k, then they have no element in common, that is, they are disjoint. And number 3, if we take the union of all these AIs, all the sets in the collection A, then that union is equal to B. If these 3 conditions are satisfied by such a collection, then such a collection is called a partition of the set B, or is said to partition B. Okay, then A is a partition of B, and the situation, as you may already know from your elementary courses in algebra towards the beginning of any abstract algebra course, say this is the set B. So the sets AI partitioning B means just this, that the sets AI divide B into disjoint non-empty subsets, the union of all of which is equal to B. So here say you have A1, here you have A2, A3, etc., many sets, and you have AK. Okay, so it's like partitioning a large hall into smaller rooms by some walls separating them. So, and the condition is that each room must have something in it. Each set is non-empty in the partition, and 2 distinct rooms have nothing, no common area between them. And if we take the grand total, the union of all the rooms, then we get the large hall back. So that is the idea of a partition. Now if we have another partition of the same set B, Here the number of sets is something else L, which may or may not be equal to K. It is some number. Another partition of B, which is not necessarily distinct from the previous partition. It may be the same thing also. Is said to refine the previous partition A, or is said to be a refinement of A if for every index j lying between 1 and L there exists an index I lying between 1 and K such that Aj prime is contained in Ai. That means this new partition is said to refine the old partition if each set in the new partition is contained in some set of the old partition. That means each new room is contained in some old room. Okay. Then we say that the new partition refines the old partition. Note that according to this definition, every partition refines itself in a trivial way, because you can take L equal to K here and Ai prime equal to Ai, then the containment is trivial. So that possibility is also there. Okay. Now finally, by this symbol where A is any set and K is a non-negative integer, we denote the set of all K element subsets of A. Okay, so that's what this symbol means, or this notation denotes. A set with K elements is called a K set. These are all things for our convenience and for shortening existing notation later on in the book. Is called a K set. A subset of some set with K elements is called a K subset. So that means if A is any set, then this denotes the set of all subsets of A that have no element, and every set A has exactly one subset which has no element, which we know is the empty set. So this is the set of all such subsets. That means it has only the empty set in it. Like that, This is the set of all one element subsets of A, or in other words, the set of all singleton subsets of A. So in set builder notation, we can write that like this. And if you have 2 here, a set of all 2 element subsets of A, and so on. So these are basically the notations and terminology we will need, which are not directly related, which comes before graph theory. Now the first section starts. In the first section, obviously we are going to start off with the definition of a graph, and then we will look at related concepts, and we will see examples to illustrate the concepts. Graphs. A graph is a pair of sets V and E such that E is a subset of this, where the meaning of this is coming from here. We will discuss what it means to avoid notational ambiguity we shall assume that V and E are actually disjoint. Okay, so now what does the definition mean actually? By the definition, a graph is a pair of sets V and E. Because we are using round brackets and not curly brackets as we use in sets, this is not an ordinary pair, this is an ordered pair, where what is the first set and what the first set is and what the second set is, that matters. Okay, so the first set is V and the second set is E. These of course are just some names given to this set. You can write A and B also, that there is no rule that you have to write the first set. You have to call it V and the second set has to be called E. There is no rule like that. Just like that, the entire entity, this ordered pair, it's not necessary that it has to be called G. You can call it H also. Okay, you get my point. Such that E is a subset of V2. Now V2, according to this definition, is the set of all 2 element subsets of V. Okay, so I think it will be better to consider an example right now, but let's just write some more things related to this definition, and then we will look at an example. The elements of V are called the vertices or nodes or even points of the graph. The elements of E its edges or lines. Okay, so the elements of the first set will be called vertices and the elements of the second set will be called edges of the graph, that from where these two sets are coming. The usual way to represent a graph is to draw points for the vertices, that is a point for each vertex. A point or a dot each vertex and by joining two dots by a line if the corresponding vertices form an edge of the graph. Let me put some ink first. Then the next important thing just how these dots and lines are drawn is irrelevant. The only information that matters is whether two dots are joined or not. In other words, the corresponding vertices form an edge or not, according to the this method of representing a graph. And one example we can immediately give. Okay, let me just wrap this part up and then we will see. We still have to make sense of that definition, that is the condition given in the definition of a graph. But before that, let's just look at this graph. Say G is equal to phi comma E, where phi has these objects and E has these objects. So according to this provision, this scheme for representing a graph, we have to draw a dot for each vertex. So these are the vertices and these are the edges according to our definition. So say we draw like this: 1, 2, 3, 4. Actually, the author has drawn things in a particular way to show some aspects of graph. So let me just draw exactly like he has drawn. So these are 1, 2, 5, 3, 4. So beside every dot, we are also going to write the vertex that is being represented by that dot. 7, and this is 6, say. I'm going to, okay, so now we have the vertices and we have drawn dots for the vertices. For each vertex we have drawn one dot. Now we have to look at the edges, and if two vertices are belonging to one edge, then we will join the corresponding dots. So for example, 1 and 2 belong to one edge as elements, of course. So I am using ruler to join 1 and 2. Like that, say I join 1 and 5 also with a ruler, and 2 and 5 also. And then 3 and 4 are also joined with this ruler. Then 5 and 7 will be joined. Here, however, I decide to use a wavy line, and 6 is not joined. That point is not joined to anything, to any dot. Okay. Now, according to our definition, the second set E has to be a subset of V2. Now, for this particular V2, or in fact for any V, this V2, the elements in it are two-element subsets of V. Now there are many such subsets. Okay, we have 1, 2, 1, 3 is also there. So if we really think about this set, then it has all these subsets: 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, then 2, 3, 2, 4, 2, 5, etc. all the way up to 6, 7. I mean, I think you get the point. We will have all 2 element subsets in this set, and E is supposed to be a subset of this. What subset, that we don't know. In this particular case, E has precisely these elements. There are many elements here in V2 that have not appeared in E as an element. For example, 1, 3 is not there. So that's why we are not joining the corresponding dots. Okay, so this is the idea of a graph, and the same graph can also be drawn in a slightly different manner. Now, before we make another drawing of the same graph, let's just see some more things about this, because the author has carefully chosen to show many aspects of a graph in this single example. You can see many things here. The first thing is that some vertices, of course, they are joined if they form an edge. They have been joined using straight lines. However, 5 and 7 have been joined using a wavy line. It does not make a difference, because we have already said just how we draw the vertices, or even their position on the plane, or it's not even necessary to have the vertices on the plane. You can have the vertices in space, or in whatever manner you can have them, you can have them. The only thing that matters is whether 2 vertices are joined or not, that is, whether they form an edge or not. So if we want, we can put a straight line here also. It will not change. I mean, the situation will not change. 5 and 7 will still form an edge, because that is an element here in E. That is one thing. Then you can see that the graph has some, you can say, disjoint parts. Disjoint in the sense that this part, which has these vertices 3 and 4 along with the edge joining them, this part could have also been drawn here. We have purposefully drawn it here as if we want to overlap the drawing with the other part of the drawing of the graph. The thing you should note is that these points where these edges are intersecting, or these lines are intersecting geometrically, they don't have any meaning whatsoever in the context of this graph, because you can draw the 3, 4 here also, then there will be no intersection. Okay, here also 3 and 4 are forming an edge. If you draw them here, then also 3 and 4 are forming an edge. 1 and 3 are not forming an edge. In that new drawing also 1 and 3 are not forming an edge. 6 is not joined to any vertex. That can happen. Okay, like for example, if you draw 3, 4 here, that will not be joined to the other parts of the graph. You can have a cyclic structure like this, where some vertices form a closed path like this. However, in some other part of the graph, the path may end. Okay, if you move along the edge from one vertex to another, then say someone starts here, then goes to 2 along this vertex, because they are joined. Okay, the movement will be made only when 2 vertices are joined along a line that is joining them. So one goes from 1 to 2, then from 2 to 5, then from 5 to 7, here the path ends. If one is here at 3, say, then one can go from 3 to 4. However, one is only restricted between 3 and 4, these 2 locations only. That's what I mean when I say that that part is disjoint from the other part of the graph. So in that sense, this particular graph has in our very naive understanding of the things, at least at this stage, we can say it has three parts. Okay, one part consists of these vertices 1, 2, 5 and 7. In what sense do they form a part? They form a part because starting from any one vertex, you can go to any other vertex following the links or the lines. If you start at 5, you can reach 7, you can go to 2, you can go to 1. If you start at 1, you can go to 2, you can go to 5 and then to 7 also. So each vertex in this part, you can start at that vertex and reach any other vertex along the links or along the lines. But you cannot reach 3 or 4 from here. So that is, it's like another island. 6 is alone. If one is trapped here, then one will stay here. Okay, so in that sense, it has 3 parts. In this vague sense, a graph can have many different parts, or it can have only one part also. Okay, that is one more point. And one, of course, I have already said that the edges can be made wavy, or it can be made quite complicated. It does not matter as long as we are maintaining the fact that these vertices are linked and some other vertices are not. So now let's draw the same graph in a different way. Draw the same graph means that is also one point that should be mentioned. It's very important. Now, without using any ruler or anything, say we have this is 1, 2, 5, 7, 6, 3, 4. So we draw like this. Say. It also represents the same graph. You should understand that although while working in graph theory or while studying graph theory, we will start to think that these pictures themselves are graphs. That is not entirely true. They are only a representation of some graph, a representation, not the representation. Okay, so these two things, they look quite different geometrically, but actually they represent the same graph, because by definition a graph is truly only a pair of two sets, okay, so of some objects that satisfy some condition, namely this one. Okay, so a single graph can have many different pictorial representations like this. But of course, if you have a picture, then looking at the picture, you will immediately see many things about the graph, which is not possible if you just look at sets like this. This a picture conveys more information about the graph at once. Right. So now we come to, so that means the graph itself is not a picture, but the picture, one picture is only one representation of a graph. Now we come to that restriction. Why do we need this restriction? But before that, let us just ask ourselves, can we have a situation where this cannot happen? Can we have two such sets V and E where, in spite of satisfying this relation, V and E turn out to be not disjoint, that is, they have some element in common? And yes, we can. And one such situation is this. Say we have V equal to 1, 2, 1, 2. V is okay. V is any set. Okay, we haven't restricted the sets V and E in any way other than the fact that they have to satisfy this relation. In fact, V can be empty set also. We will discuss about that, but let's just first see this thing. So this is a legitimate set. According to set theory, it's a legitimate set which has 3 elements. One of the elements is itself a set, but we do not bother it. They can be anything, any sort of objects. Okay. Now, is this E satisfying this? Let us see. According to our relation, every element in E has to be a 2-element subset of V. What about this element? It's a 2-element set. That means it's a 2 subset. According to the terminology that we have agreed on, it's a 2 subset of V. Why is it a subset? Because the elements in this subset are also there in V. That is what I am trying to say is this. It's a subset of V and it has 2 elements. What about the other element in E? This is also a subset of V and it has 2 elements. The first element is in V as an element. The second element also is in V as an element. So yes, this relation is satisfied. So as far as satisfying this relation is concerned, we can call it a graph, except here V and E are not disjoint clearly because this object belongs to both V and E. Now here the situation is somewhat complex. Whether you want to call this object a vertex or an edge, you actually, according to our the things we have said, it is a vertex as well as an edge. Now such a situation we do not really need in the study of graph theory that we are going to embark on. We don't need this situation. That's why we are assuming that V and E are disjoint. By putting this extra restriction, we are not really losing too much generality, because this type of complicated situation where the vertex and the edge set are not disjoint, that we don't really need. Okay, so we chuck them out of our discussion by assuming this extra condition. Okay. Have I left anything else? I mean, have I missed anything else about this figure that I wanted to talk about, because this is the time? Now this cyclic structure that I was saying, talking about now, this may not be present, of course. In a graph, you can have one pictorial representation of a graph like this, say, where you don't have any cyclic structure. Although this graph, unlike this one, has only one part. Every vertex, you can start at any vertex and you can reach any vertex. Okay, so let's move on. have I really said that the set V is called the vertex set and the set E is called the edge set? I doubt I have. If I haven't written that, you just write that the set V, that is the first set in the graph, is called the vertex set of the graph. In fact, let me just write. This should have been written before presenting the example. The set V is called the vertex set and the set E is called the edge set of the graph G equal to V comma E. So they have names now. These sets have names with respect to a graph. A graph with vertex set is called a graph on V. We need such a thing because you can have many different types of graphs, many different graphs on a single set as their vertex set. Okay. For example, the example that we considered before this, there the vertex set of the graph is this. Taking this same set as the vertex set, you can have another graph where the edge set is different to represent the fact that the other graph also has this set as the vertex set. We will say like this, that any graph with this vertex set is called a graph on V. There are many things. Let's go through them one by one. The vertex set of a graph G is referred to as V of G, and the edge set of G is referred to as E of G. You probably now understand why we are calling the sets V and E, because vertex and edge. These notations are independent of any actual names given to these sets. For example, So we have already said that there is no need to always write G, V and E. We can give different names to them, and we will need to because we have different types of graphs. So say our some graph is called H and its vertex set is W and H set is F. So these are names given to the vertex set and H set of F. So the vertex set of this graph will be denoted by V of H, not by W of H. That's what we are saying, that this notation is independent of the names of the vertex and edge sets. Okay. When it comes to denoting the vertex set of a given graph, then we will invariably call it V of that graph, edge set E of that graph. So here this of course is not true. I mean, we are not using this. This has no meaning. V of H is equal to W and E of H is equal to F. And now some relaxation. We shall not strictly distinguish between a graph. Yeah, we shall not always distinguish between a graph and its vertex set or edge set. For example, if V is a vertex of graph G, we shall write V belonging to G to express this fact. Instead of writing actually this is the correct notation, we should write V belonging to V of G, but we shorten the notation because if we keep on writing everything, then the notations will become unwieldy. We won't be able to work with them conveniently. If E is an edge of G, then we shall write just like that, somewhat casually, that E belongs to G instead of writing the correct one, that E belongs to E of G. This reduces our writing time and labor, and so on. Okay. The number of vertices of a graph G is, hold its order, and is denoted by this notation. Okay, number of vertices of a graph. That means it's the cardinality of the vertex set. This thing. It may be finite, it may be infinite. So those possibilities are there. The number of edges of G is denoted by this symbol. In some texts, the number of edges is called the size of the graph. However, in this text, the author has not said anything like that. Okay, so the number of vertices is order, the number of edges is size. But for us, we only apparently need only order. Diestel hasn't said anything about size. Maybe later on in the book he has said, I don't know. So we will see. A graph is called finite infinite countable etc. according to whether its order is finite, infinite, countable, etc. So a graph is called finite if its order is finite. It's called infinite if its order is infinite. Countable if its order is countable. So everything depends on the cardinality of the vertex set or the order. Okay. Except in chapter 8, all our graphs will be finite unless stated otherwise. In other words, we will be mainly dealing with finite graphs. Infinite graphs we will consider only in chapter 8. Okay, for the empty graph where both the vertex set and the edge set are empty. Note that this restriction that we have put on E forces E to be empty when V is empty. Because if V is empty, then the set of two element subsets of V is also empty, and E being a subset of that must also be empty. So we have this situation, this possibility within our definition. For the empty graph, we simply write the symbol for the empty set. So when we say graph this, it means the empty graph. a graph of order 0 or 1 is called a trivial graph. So if a graph has no vertex at all, which is this case, then also it is called a trivial graph. Or if a graph has only one vertex, in which case it has no edge, because according to our definition of an edge needs at least two vertices. To form an edge, you need at least two vertices. So if there is only one vertex, so there is no possibility of an edge. So in that case, the vertex set is a singleton set and the edge set is empty. So that graph is also called a trivial graph. Now the thing is this, the author writes, sometimes while starting an induction, we will need a trivial graph. At those times, trivial graphs will be useful. At other times, they will form counterexamples, some silly counterexamples to some theorems that we will be discussing. Say something happens for all graphs except for the two trivial graphs. Okay, so in such cases they become an annoying occurrence, a nuisance. So we will treat trivial graphs with a generous disregard. We will use them when we need them, other times we will just forget about them. Because otherwise, if we continue to consider trivial graphs everywhere where we discuss about general graphs, then all the results will have to be supplied with unnecessary non-triviality conditions. Say something happens for this class of graphs, provided it's not trivial. So to avoid that, we will simply forget about trivial graphs at all if they don't satisfy a given property. If something has been said about graphs which is not true for trivial graphs and nothing else has been said in the statement, then that will mean that we have disregarded the trivial graph there. A vertex V is said to be incident on an edge E if V belongs to E. Because E, according to its definition, is a two-element subset of the vertex set. So a vertex, it makes sense to ask whether a vertex belongs to that two-element subset or not. For example, in the example that we consider, this is an edge. So the vertex 1 belongs to this. So we will say that 1 is incident on this edge. 3 does not belong to this. So 3 is not incident on this edge. Okay, so that is the definition of a vertex being incident on an edge. In this case, we also say that E is an edge at the vertex V. Okay, so in that example, 1 comma 2 is an edge at the vertex 1 and it's also an edge at the vertex 2, but it's not an edge at the vertex 3. So these are some ways of saying these things. The two vertices incident on an edge are called its endpoints or ends. The bad thing about graph theory is that in the very beginning itself there are many definitions, but the good thing at the same time is that the names that come up in this definition, that is the terms, they are so natural that they are very easy to remember. You can see that two vertices incident on an edge are called its endpoints, which is very natural. Say if this is an edge, these are two vertices, or more strictly speaking, if this is an edge, then these two vertices are called its endpoints or ends, which is quite natural. It's natural to call them ends. You can see that from the figure. And an edge is said to join its ends. So we will say that the edge 1, 2 joins the vertices 1 and 2. An edge whose ends are x and y is usually written as xy or yx. This is also a simplification of the notation. Instead of writing it as a set, we can simply write it as xy. Okay, we need, in the actual definition, we of course need the fact that this is precisely what it is. Okay, it's a two-element subset of the vertex set, but we can convey the same information by simply writing xy or yx, which clearly shows that its ends are x and y. If x belongs to x and y belongs to y, then xy is called an xy edge. So say you have your vertex set, then in the vertex set you find two subsets. Say this is your vertex set V equal to 1, 2, 3 in a graph, and say you have 1 here, 2 here and 3 here, and suppose the graph is like this. That is, the edge set consists of the edges 1, 3 and 2, 3, or the two element subsets 1, 3 and 2, 3. Then if this set is called x and this set is called y, then the edge 1, 3 is an xy edge, and so is the edge 2, 3. When you say that xy is an xy edge, then it means that this is coming from this set and this end vertex is coming from this set. So you have to be careful in saying that this is an xy edge. Here the order matters. Now if you change the order, then things may not work out, because x and y may be different sets. You cannot say that yx is also an xy edge all the time. This will be useful when, say, you have to consider a graph in which say you are studying some particular edges which happen to have their endpoints lying on some sets. Then their collection may be called the set of all xy edges, where x and y are appropriately chosen sets. The set of all xy edges in a set E, in an edge set E, is denoted by E of x comma y. So E of x comma y will consist of all the edges which have each one of which has one endpoint in x and another endpoint in y. And here also some further simplification in the notation. Instead of writing E of x comma y, say if your first set has only one vertex, and E of x comma y we shall write E x comma y and E x comma y respectively, and the set of all edges at one vertex, the set of all edges at the vertex, at some vertex V, is denoted by this symbol E V, that is all the edges at V. For example, in this graph, 1, 2, 5, 7, 3, 4, 6. Do you see how quickly you can represent a graph using a diagram instead of writing those sets? That's why these diagrams are so useful. In this graph, E of 1 is the set of these two edges which are incident on which are edges at the vertex 1. One is incident on this edge and one is also incident on this edge. So that means this is 1, 2 and 1, 5. If you want, you can also write 1, 2 and 1, 5. In the context of this graph, they will be meaningful because of this simplification. Like that, E of 5 will have 3 edges, 1, 5, 2, 5 and 5, 7. So you get the idea. Then next, two vertices x and y of the graph G are called adjacent or neighbors if xy is an edge of G. So if we look at this graph itself, 1 and 2 are adjacent because this is an edge. 1 and 7 are not adjacent, though you can reach from 1 to 7 through these two edges, but they are not adjacent because 1, 7 is not an edge in the graph. 6 is not adjacent to any of the other vertices. And note one more thing, that according to the definition of our graph, I forgot to tell you about this. You never see anything like this, a vertex being joined to itself, because in the definition we have required E to be consisting of two element subsets of V, not one element subsets. Okay, so there is no possibility of having a loop where an edge starts at a vertex and ends at that same vertex. According to our definition, each edge must have two distinct endpoints. One more thing is there, we cannot have multiple edges with the same endpoints. That idea is there in a multi-graph. I think I forgot, I studied these things long ago, but we will see. In multi-graphs, those multiple edges are allowed. Okay, so if two vertices are joined by an edge, or if they form an edge in the graph, then they are said to be adjacent, or they are said to be neighbors. Two edges say E and F, which are distinct, are said to be adjacent if they have a vertex in common. If they have an n vertex in common. For example, these two edges are adjacent, 1, 2 and 2, 5. The n vertices of 1, 2 are 1 and 2. Those of 2, 5 are 2 and 5. So 2 is a common n vertex. So these two are adjacent. Pictorially, two edges are adjacent if they are touching at one end. 1, 2 and 5, 7 are not adjacent because there is no common end. 1 and 2 are entirely different from 5 and 7. So these are the concepts of two vertices and two edges being adjacent. If all the vertices of a graph are pairwise adjacent, then it's called complete. So if in a graph, say I'm going to draw a graph here. Here say the vertex set is having 3 points. One more thing I should say at this point, it's not necessary to always take numbers. You can take in fact any objects, tables, chairs, anything whatsoever. We are not putting any restriction on the type of objects that we can have as its elements. Numbers are convenient, so we are just using numbers. If in a graph all the vertices are pairwise adjacent, that means if you choose any two distinct vertices, they are adjacent. If that happens, then such a graph is called a complete graph. So for example, 1 and 2 are adjacent, 1 and 3 are adjacent, 1 and 4 are adjacent, 2 and 3 are adjacent, 2 and 4 are adjacent, and 3 and 4 are adjacent. So this is a complete graph on 4 vertices. In a complete graph is complete in the sense that it has as many edges as such a graph can possibly have. Okay, this is clearly not complete because here, for example, 1 and 7 are not adjacent. It can be made complete by putting additional edges that are missing. But in a complete graph, the number of edges is the maximum that is possible for that particular graph. I mean for that particular number of vertices. A complete graph on n number of vertices is denoted by this symbol kn. Some people write this n as a suffix, but here the author has decided to write n as superfix. A K3 is called a triangle. Now there are some things we should say at this point. Why AKN? For example, this is AK4. Why not BKN? That's because, strictly speaking, you can have another graph, complete graph on 4 vertices, where these are the vertices, and clearly, of course, the graph will look like this. Strictly speaking, these two are different. In fact, let's just give them different names also. Why? Because the vertex sets are different. So actually V2 is not equal to V1, but the graphs look similar. So that's why each one of them is called a K4. It just conveys the information that any two distinct vertices are adjacent. That's all. A K3 is called a triangle. So a K3 looks like a triangle, that's why it's called a triangle. It's not the same as the triangle from plain Euclidean geometry. Okay, a K3 may look like this, or it may look like this also. Or it may even look like this. Note that here also any two distinct vertices are adjacent. pairwise non-adjacent vertices or edges in a graph are called independent. So for example, in that example that we have been taking again and again, say 1, 2 and 5, 7 are independent edges, 1 and 5 are independent vertices, but it's not necessary to take only 2 objects. You can have a set of objects. More formally, independent or stable, that is also another term that is used here. More formally, a set of vertices or edges is called not a mixture, okay, either a set of some vertices or a set of some edges, not that we are considering vertices and edges together. Or maybe I think we can consider also, because no, we cannot consider vertices and edges together. Why? Because adjacency is there between 2 vertices or between 2 edges, but between a vertex and an edge we don't have adjacency, we have incidence. Okay, so that's why we cannot consider them together here. A set of vertices or excuse me, is called independent if that same condition, if no 2 of its elements are adjacent. Independent or stable if are adjacent. Okay, next we come to a somewhat more advanced idea. Let G equal to V comma E and G prime equal to V prime comma E prime be 2 graphs. Now we say that one is isomorphic to the other. We say G is isomorphic to G prime if there exists a bijective map. Some ink is needed. a bijective map or a bijection f from V to V prime, okay, such that bijection means it has to be both injective and surjective, or one-to-one and onto. For all vertices u and v belonging to V, we have uv belonging to E if and only if fu fv belongs to E prime. What does it mean? It means that two graphs are said to be isomorphic if and only if there is a bijection between their vertex sets, such that two vertices in one graph form an edge if and only if their images in the other graph also form an edge there. It's the same idea of a structure preserving map between two, say, algebraic structures. Say you have two groups, you have they are said to be isomorphic if and only if there is a bijection between the sets that preserve the algebraic structure. That is, say you have two groups G1 and G2, and you have a bijective map between them, such that for any two points in the first group or any two elements in the first group, if you compose them using the group operation in the first one and then on that you apply f, that is the same thing as first applying f on the elements individually and then composing the images in the second group. The results are the same. So this is preserving the algebraic structure or group structure. This is preserving the graph structure. That is, it is preserving adjacency. Okay, if two vertices in the world of the first graph are adjacent, then their mirror images in the world of the mirror graph are also adjacent there. Okay, so that is the thing. Then they are said to be isomorphic, and just like isomorphic groups, isomorphic graphs are also not considered to be different. They are the same thing, the same graph actually, just they have been named somewhat differently. It's like having those two k4s, okay, where you have in one of them, if the vertex set has the vertices 1, 2, 3, 4, in the other the vertices have been given just different names A, B, C, D. You can set up a one-to-one correspondence between the vertex sets. Clearly, any one-to-one correspondence, you will see that two vertices are adjacent in one if and only if their images are adjacent in the other, which is quite easy to see for the K4 graphs. Such a map F is called an isomorphism. If G is isomorphic to G prime, we express that by writing this notation. G is isomorphic to G prime. If G is equal to G prime and you have such an isomorphism, which is not necessarily the identity map, okay, you can have other isomorphism also from a graph to itself, then an isomorphism between them is called an automorphism of G, just like the case with groups or vector spaces, or in fact any such structure. You have the idea of automorphism of a graph, of a single graph. We do not normally distinguish between isomorphic graphs thus we may write G equal to G prime rather than this. So although strictly speaking G and G prime may be different graphs, but if they are isomorphic we treat them as the same graph, because as far as graph properties are concerned, as far as adjacency of vertices is concerned, there is no distinction, real distinction between isomorphic graphs. They are just two ways of looking at the same information, because if you really think about it, I mean, you get my point. It's just like group isomorphism. Thus, we may speak of the complete graph on 17 vertices, etc. All complete graphs on 17 vertices are isomorphic to one another, which is rather easy to see. A class of graphs that is closed under isomorphism is called a graph property. So if you have a class of some graphs, say, then if you apply closed under isomorphism means if in that class you apply some isomorphism on one graph, you end up with another graph. That graph also happens to lie on that class. That's what we say by the graphs being, or rather the class of graphs being closed under isomorphism. Then such a class represents a graph property. Here the author writes somewhat vaguely that such a class of graphs itself is called a graph property, which also makes sense, but they represent a particular aspect of those graphs that remain constant, it does not change in that class. If one particular graph has some property, then all the other graphs in that class will also have that property. So that class collectively represents that property. For example, containing a triangle is a graph property. Containing a triangle means what? It means that you find a set of 3 adjacent vertices in your graph. 3 vertices in your graph that are pairwise adjacent. For example, in the graph in our example, this is a graph containing a triangle. Okay. If G contains three pairwise adjacent vertices, then so does every graph isomorphic to G. This is clear because if you apply an isomorphism to such a graph, this is only one example, you will have many different graphs containing a triangle. If you apply an isomorphism to such a graph, then all the vertices will change. They will be mapped onto some 3 other things. In that graph also, those 3 other things will be pairwise adjacent, forming a triangle there. So that's why containing a triangle is a graph property. A map taking graphs as argument and is called a graph invariant. If it produces the same value for isomorphic graphs. So say you have a mapping whose input is a graph, the output may be anything. Okay. Now if you are as argument, if you put one graph and then the output is something in that map, and you put another graph in that map as input, that is isomorphic to the previous graph, then you get the same output. If this continues to happen, that is the function generates the same value for isomorphic graphs, then that such a function is known as a graph invariant. Such a function must have its input a graph. output may be anything. It may be integer, rational number, it may not even be number, it may be some other graph also. Okay, so if that stays the same for isomorphic graphs, then we call such a function a graph invariant. The number of vertices and the number of edges of a graph are two very simple graph invariants, and the greatest number of pairwise adjacent vertices is another. If you think about it, say your function calculates the number of vertices in a graph. So you input in that function a graph. It calculates the number of vertices. Okay. You give as input another graph isomorphic to this graph. So the number of vertices should be the same, because for the two graphs to be isomorphic, first of all, there should be a bijection between the vertex sets. So the number of vertices should be the same. Like that, if you go into the definition of an isomorphism, you will see that the number of edges should also be the same for isomorphic graphs. So these are two very simple invariants. The greatest number of pairwise adjacent vertices is another. Say in this case, it's actually a generalization of this property. For this particular graph, what is the maximum number of pairwise adjacent vertices? 3, because you don't have any larger complete graph inside this graph. I mean, as a part of this graph, that maximum number is 3. If any other graph has a triangle like this, then there also the maximum number of no, what I am saying is this. No, not having a triangle. If you consider another graph isomorphic to this graph, yes, then there also the maximum number of pairwise adjacent vertices will be 3. So that is another graph invariant. After this we have operations on graphs, but I don't think I'll be able to cover this much in one video. So let's just end this here, and in the next video we will continue. We will finish this basic definitions and concepts, and then we will move to the second section, 1.2, where we will study about the degree of a vertex and such concepts, and there only we will look at some theorems, some results. Okay, so with that I end this video for tonight. If you have any doubt regarding these things, see, we have gone through these things quite sketchily because these are some initial things and this is a graduate level text. So here we will not dwell more on these things than this much. Okay, but starting from section 1.2 we will actually have results and we will have the study done properly. So I sign off with that. This is me, Lucifer, from a mathematical room. Have a nice night.